switch it up a bit. Today we're actually doing a total rebrand, and we're pivoting to calling the channel ASMR with Mr. Volel, where the M, of course, stands for math. On today's episode, we're going to be solving some word problems using systems of equations. So grab yourself a nice comfy blankie, a good pair of headphones, and get settled in, because it's going to be an extra satisfying one today.
All right, that's enough. Hi, friends. Welcome to our 10th class of Unit 5, where I have not lied to you. We are going to be continuing to do some problem solving with systems, part 2. So, last time, we continued along using our 5-step procedure for solving some word problems. Keep those 5 steps in the back of your mind. Let's get right into it and see how it can maybe help us solve some problems like this one. You're making your on-stage debut in a school play, and the whole family has decided to show up and show out. And by the whole family, I mean the whole family. The school sells tickets online for $10 and at the door for $15. Between the 35 members of your family that came to the show, they spent a total of $415. How many of each type of ticket did your family members purchase? Cool. So again, think of your 5 steps. Do I need a diagram? What are my variables? What am I solving for? Do I need a chart to keep track of a particular relationship? What is the system of equations going to be that I need to solve? And how can I make sure that my answers make sense in context? Take a risk, take a chance, take a gander. You've got 2 minutes. See how far you get. Go, go, go. And stop.
And if it's not an ASMR, I don't want it.
All right. I don't particularly need a diagram here. I could draw a stage, but that's not really going to help me solve. Let's start with our variables. I'm interested, looking at my last sentence, in knowing how many of each type of ticket was purchased. So I'm going to need 2 variables, one to represent the number of online tickets and one for the number of at-the-door tickets. I could choose O for online, but notice O is easily confused with 0. I'm going to pick something like N. You could use X, you could use whatever you want. I'm going to say N is going to represent the number of online tickets that were purchased. And then I'll use something like D for the number of at-the-door tickets that were purchased. From here, no particular relationship that I need to use to my advantage. Let's build our equations. Looking here, I know that online tickets are $10, at-the-door tickets are $15, and in total, we've got $415. So what that tells me, hopefully, is that if I have $10 per online ticket, and I multiply that by the number of online tickets that I sell, there's the cost from online tickets, plus $15 per at-the-door times the number of at-the-door, there's the amount we got from at-the-door tickets. Adding those 2 amounts together should give me my $415. And for my second equation, I know that we bought 35 tickets in total. So the number of onlines plus the number of at-the-doors should equal 35. There we go. There's our system. You can solve this using either substitution or elimination. I think I did elimination first last time, so I'll do substitution first this time. Let's say that I want to get N by itself in the bottom equation. So I'll start by subtracting D from both sides. That tells me that N is equal to 35 minus D. From here, I can now take this guy and substitute into my top equation. Doing so, I have 10N, but N, of course, is interchangeable with that 35 minus D from the bottom equation, plus 15D is equal to 415. Starting off by doing some distributive property, 10 times 35 is 350. 10 times negative D is negative 10D, plus 15D equals 415. Notice I've got some like terms on the left side that I can combine. This would give me 350 is equal to, or not equal to, sorry, but plus 5D. That is equal to 415. And from here, I'll start by subtracting 350 from both sides to get closer to isolating my variable. That tells me that 5D is equal to 415 minus 350, which is 65. Last but not least, we'll divide both sides by 5. that tells me that D is equal to 65 divided by 5, which is 13. Last but not least, I now need to take this value of D and use it to find the value of N. So I can take this guy and right over here, substitute in. Knowing that N is equal to 35 minus D, we have just established that D is equal to 13. That means N is equal to 35 minus 13, which is 22. Last but not least, I've got my answers, but I'm not quite done. In context, I need to include some units. So that tells me that I sold 22 online tickets and 13 at the door tickets. Yay! Let's do another. A bodega cat has spent the past several months secretly hoarding a stash of loose change. In that time, the cat has accrued a small fortune of $2.10 in nickels and dimes, with a total of 27 coins in its collection. How many of each type of coin does the cat have in its possession? Now, this kind of problem is a little bit interesting because there's some information hiding in plain sight. I'll tell you it might have something to do with nickels and dimes. How can you use the fact that you're working with nickels and dimes to build at least one right equation in our system? What do you think? What are our variables? What are our equations? And if you're feeling real confident, try and solve. Take 2 minutes, pause the video, go, go, go. And stop. All right, let's do it. So again, no need for a diagram here. Let's start with our variables. I want to know how many of each type of coin my cat has. Well, I've got 2 types of coins, so I'm going to need 2 different variables. Perhaps as an interesting coincidence, my variables, I'm going to choose them to be the same. So I know how many tells me I want specifically the number. So I'll say N to represent the number of nickels in my cat's possession, and D to represent the number of dimes. Now, if we're thinking about building some equations, at least one of them should be hopefully kind of obvious. We have a total of 27 coins in our hoard. So that means if I add the number of nickels to the number of dimes, that should be equal to 27. For the second equation in our system, though, something about nickels and dimes is important. It has to do with the fact that we've got $2.10 in total. Well, if you've played with money or you know anything about money, it's important to know the value of a nickel and the value of a dime to solve each problem. Well, every nickel is 5 cents and every dime is 10 cents. I could think of these as fractions of dollars, but I think working with cents is going to make our lives a little bit easier. Notice $2.10, I could think about that as cents as well. Well, $2, $1 is 100 cents, so that would be 200 cents plus my 10 cents. This is equivalent to 210 cents. So with this information in mind, now I'm in familiar territory. I know that the value of 1 nickel is 5 cents, times the number of nickels that I have, that will give me the amount in nickels, plus, same logic, 10 times D for the number of dimes, right? That should give me 210 cents in total. Would you look at that? There's a system that we can solve. I'm going to choose to solve this guy using elimination, because last time we did substitution. So from here, I'm going to take, in a controversial twist, my bottom equation. I don't need to multiply. What if I take this entire bottom equation and divide it by 5? So I'm going to divide the entire bottom equation by 5, and when I do that, I'd get here, right? N plus D on the top is going to be equal to 27. Dividing 5n by 5 would leave me with n. Dividing 10d by 5 would leave me with plus 2d. And then 210 divided by 5, that's equal to 42. And now, would you look at that, I've got 2 n's here that I can cancel out by subtracting. N minus n is n. D minus 2d is negative d. And then 27 minus 42, well, that's negative 15. If negative d is equal to negative 15, then positive d should be equal to positive 15. Knowing what the value of d is, I can now find the value of n. Well, I know n plus d from the top equation is equal to 27. We've just found that d is equal to 15, so n plus 15 must be equal to 27. Subtracting 15 from both sides to isolate our n tells me that n is equal to 12. So I've solved my system. Last move, in context, that means we've got 12 nickels and 15 dimes in our kitty corner. Cool! One last one for the road. Let me introduce you to one last type of system word problem. Remember back in Unit 1, Unit 2, Unit 3, we did a couple where we were talking about some trips that we took and the amount of time that it took, the distance we traveled, how fast we went. We can also solve problems like that using systems. Craving some adrenaline, an alien takes its flying saucer out for a joyride, making the 600-mile journey from Area 51 to Albuquerque. Traveling with the wind as a tailwind, the trip there takes only 4 hours. On the way back, working against the wind as a headwind, the trip's duration increases by 1 hour. We want to know what are the speeds of the flying saucer and the wind. So, we'll do this one together, but before we do, can you remember what the important relationship is that is going to connect all of these pieces of information? We're traveling 600 miles. We want to know the speed that we're traveling. We know the amount of hours or the time it takes for us to get there. What formula are we working with here? Go, 10 seconds. 5, 4, 3, 2, 1, and stop. Very good. We know that if I take the distance that I travel, it's equal to the rate or the speed at which I travel times the amount of time that it takes for me to travel. So here we can set up our first chart of the unit, and the crowd goes wild. So from here, I need to figure out what my two cases are. Well, before I do, let's define my variables. I want to know what the speeds of the saucer and the wind are. So my two variables here, specifically I'm interested in the speed of the flying saucer. I'll choose f as my variable, just so I don't confuse s with a 5, for example. So I'll say f is specifically going to represent the speed of my saucer, where w will represent the speed of my wind. From here, I've got two cases. I have one where I'm traveling with the wind, so the wind is acting as a tailwind. We'll call that our blue case. And then my green case will say on the way back, the wind is our headwind. It's working against us. From here, see if you can take a minute, pause the video. What's going to go in each column? What's the distance? What's the rate? And how much time does it take? See what you come up with, and then we'll chat. Go, go. And stop. So in both cases, notice that we're taking a 600-mile journey. So both cases, our distance is 600 miles. As a tailwind, the wind is pushing us. So whatever the speed of our flying saucer is, when the wind is working with us, notice the wind will be adding to our speed. So here, the rate would be the rate of the saucer plus the rate of the wind. When it's working against us, though, as our headwind, it's going to be detracting or subtracting from our speed. So we've got our rate column filled in, and now for our time. For my there case with the tailwind, I know that it took me 4 hours to get there. On the way back, it increases by 1 hour. 1 hour more than 4 hours would be 5. And would you look at that? From here, I can now build my system of equations. In my first case, I know the distance, 600, is equal to my rate of f plus 4 times, or f plus w times 4. So f plus w times 4, to make sure the entire f plus w gets multiplied, I'll write it in parentheses. By exactly the same logic in our bottom equation, 600 will also be equal to f minus w times 5. To make sure the entire f minus w gets multiplied, I'll again write it in parentheses like so. From here, there's no right way to solve. I'm going to choose to do it by elimination. Using the same strategy above, notice that I can take each equation and not just multiply, but divide by the same number. Let's say that I want to get rid of those pesky parentheses. One way that I could do that, of course, would be to distribute. But if I want to get rid of that multiplication by 4, I could also just start by dividing the entire top equation by 4. By exactly the same logic, I'm going to start by, instead of multiplying, dividing the entire bottom equation by 5. Doing those divisions, I end up with the following system. 600 divided by 4, if you check with a calculator, why did I say it like that? 150. 150 times 4 is equal to 600, so 600 divided by 4 is 150. And then notice dividing by 4 on the right side gets rid of the multiplication by 4. That just leaves me with my f plus w. And then on the bottom, if I take 600 and divide it by 5, that would leave me with 120. And then that cancels out the 5 on the right side, which leaves me with my f minus w. From here, I think the easiest move to make is to do some elimination. We did subtraction in the one above. I will add them over here. To give myself more space, I'm going to pull this up to the right. So doing my addition, 150 plus 120, that's going to leave me with 270. I have f plus f, that's 2f. And then I have w plus negative w. Notice those will undo each other. So from here, I know 270 is equal to 2f. All I've got to do is divide both sides by 2 to get that f is equal to 135. From here, all that's left for me to do is find w. Notice I can take one of my two bottom equations. I'm going to choose the one on top. I'll say 150 is equal to f, which we've just established is 135 plus w. To get w by itself, all I need to do is subtract that 135 from both sides. These guys go away on the right. 150 minus 135 is 15. So in context, I've solved my system. That means that it takes me, or I travel, right, at 135 miles per hour, my alien's saucer. And then the wind is at a speed of 15 miles per hour.